Good afternoon, everybody, and welcome to our MOS Live streaming here from the Museum of Science and at home. My name is Karen. I'm one of the many educators here at the Museum of Science, and today I'm going to be acting as your moderator. All this means is I'm going to be keeping an eye out for all of your observations and your comments and your questions, and I'll be passing them along to our lead educator, Talia, who you will meet momentarily. Now, if you do want to ask a question or make an observation, just find the Q&A box down at the bottom of your Zoom window and click on that and type in your answer and they'll come straight to me. If you are watching us today on Facebook or YouTube, unfortunately, we cannot field questions or comments from those platforms. And lastly, today we're using our auto transcript captioning right through Zoom. So apologies if it does not exactly match what we are saying. We are trying our best. Our live captioners were unavailable today. If you do want to turn off those subtitles, you can just click on the CC button and choose hide subtitles. But I think with that, it is time to meet Talia. So come on video and introduce yourself.
Hello, everybody. As Karen said, my name is Talia. I use she, her pronouns, and I'm going to be your educator today. So we are in week 3 of Galaxy Month here on MOS Live. And so last week, my coworker Katie talked about all the different types of galaxies there are. The many different forms we see, including some like this, the beautiful spirals, the giant elliptical galaxies, the fluffy irregular galaxies, and the oddball lenticular galaxies. And so the question is, some of these are very small. Irregular galaxies are often quite small. Spirals and ellipticals, however, can be really, really big. So how do they get that big? Like, how do galaxies even start? How do they form? That's what we're here to talk about today. We're here to talk about how galaxies grow and evolve. And if you want to see a brand new galaxy forming today, well, it doesn't really happen in today's universe. At the point in the universe where we're at today, you're not really seeing brand new galaxies forming out of nothing. So if you want to see galaxies forming, you have to be able to look back in time. Fortunately for us, astronomy is basically the only science where you actually can look back in time. All you got to do is look really, really far into the distant visible universe, and you're actually looking back in time at what was going on when that light was first emitted. And we can actually go all the way back to very, very early in the universe's history. This delightfully colorful tie-dye pattern, what you're seeing here, this is the cosmic microwave background. And it's all over the sky. This picture covers the entire sky. And what it is, it's radiation. Not the kind that, you have to worry about turning you into the Hulk or anything like that. So nothing that you need to worry about. But it's radiation that's in every direction, which means it's very, very faint. It's very, very old. And that we think it comes from actually the Big Bang. This is sort of the leftover radiation from the Big Bang. And the important thing here is that it's not completely uniform. It's not the same all the way across. Where you're seeing those little color variations, those were where there were little temperature variations very, very early in the universe's history, a few 100,000 years after the Big Bang. I know that sounds a lot like a long time, but not as universes are measured. So these colors indicate temperature differences, with the red indicating places where it was just a few degrees hotter, and the blue, the dark blue, being where it's a few degrees colder. And this is important because if you think about an ice cube, for instance, or anything solid, always takes up less space than the liquid or gas forms, with the actual exception of some things like ice water. Actually, ice can be a little bigger, but it means that it's easier for things to come together and compact together where it's cold. So those dark blue areas, those are where matter could start to come together. That's where you could start to get baby stars and the little seeds of what would become galaxies. So by looking at this big, huge picture of the background radiation of the birth of the universe, we can already see where it's likely that you're going to get the first galaxies starting to form. And we also have really good telescopes that can actually see young galaxies. Of course, probably the most famous telescope, well, let me ask you that. What do you think is the most famous telescope out there? Go ahead and put your answer into the Q&A.
I have a guess, but I'll wait to see what our friends' guesses are. I got one guess and another. So far, they're both for Hubble. See if any more come in. Another for Hubble.
It's kind of I asked them what they thought the most famous, and I agree with them. I think it's Hubble. I think Hubble is the most famous, and Hubble is right now the telescope that has seen the farthest out towards the edge of the visible universe, which means it's seen the oldest galaxies that we've ever seen, and has it as its current record holder. So what we're looking at here is the northern sky. Here's the Big Dipper, the familiar shape of the Big Dipper. And what Hubble did is you may have seen pictures of its famous deep field. So what that is it looked at one little patch of the northern sky for a long period of time and got a lot of detail. So what we're doing now is zooming in to the Hubble deep field, this region that Hubble looked at extraordinarily closely. And within that deep field, there was a little red smudge. And that little red smudge, this little tiny red smudge, this is the current record holder for the farthest galaxy we've ever seen, which makes it the oldest galaxy we've ever seen. We're seeing this galaxy when it was quite young. So this is how we can actually look back in time and see what galaxies looked like when they were first young and still starting to form. This one doesn't have a fun name. Its name is GNZ11. But this galaxy, we're seeing it the way it looked about 400 million years after the Big Bang. So at this point, the universe, the whole universe is only about 400 million years old in the era that we're seeing this galaxy. And again, that sounds like a very long time, but again, not as universes measure time. This is very, very early in the universe's history, and we're looking at this little tiny galaxy compared to the Milky Way, but it's already pretty big. So we know from this that there were galaxies forming within the first few 100 million years, and that they were already getting pretty big. This one is about 1% the mass of our Milky Way today, but it's undergoing incredibly fast star formation. It's making stars 20 times faster than the Milky Way is today. So even though it's smaller than the Milky Way, it is still pretty big for being such a young thing, and it's generating a lot of new solar systems inside of itself very, very early in the universe's history. So we still haven't been able to see that very earliest era when the galaxies are actually beginning to form, because Hubble can't see that far. We're hoping that the James Webb Space Telescope, which is due to launch later this year, will be able to see farther and give us a few more details. So that's how these galaxies are at least beginning to form within their first few 100 million years. And they're pretty small, but they're bigger than we thought they would be at this point in the universe's history. So very, very early, you're getting pretty big galaxies, but they're not nearly as big as the galaxies we see today. So then we have to ask the question, how do they get to be the big, huge galaxies that we see today? If they're starting off as these things that are like 1% the size of the Milky Way, how do you get to something as big as the Milky Way? And there are galaxies out there even bigger. So that's my question for you. How do you think these galaxies get bigger? Anybody can feel free to take a guess. You can always put question marks if you're not sure. But what do you think?
Yeah, question marks and unsure. We love that in science. It just means that you are seeking more information. So if that is your answer to Talia's question, that is a fine thing to put in the Q&A box. So far, I haven't gotten any guesses. Oh, here's one that just came in, combining with other galaxies. See if any more come in. More stars get made, making the solar systems and the things inside it bigger, question mark? So a suggestion, but also a maybe. I'm not sure, but maybe the gases.
And those are actually all related. So it sounds like they're totally different answers, but actually
also,
all three of those.
Kudos to the friends willing to put themselves out there. I always appreciate it when people answer our questions. So want one more?
So
one more suggestion?
Yeah, sure.
The more energy stars produce, and perhaps the galaxy uses the energy to get bigger, says a third grader.
All right. So we're not sure exactly. Some galaxies may just start off very big. Like, again, we haven't seen that very earliest era, but we know most of them don't. And so they have to grow somehow. And it's sort of a combination of all the things you guys have been talking about, especially the idea of galaxies combining together, galactic collisions, which happens a lot. This is an image of two galaxies colliding with each other. We call this the antenna galaxy, and it's actually two galaxies coming together. So this has to do with the fact that the galaxies have a lot of mass in them. Especially these ones that are have huge gas clouds in them, and they're generating lots of star formation. These have a lot of mass, which means they have a lot of gravity. Two things out in space, if there's not much else pulling on them, they're going to come together. That is true for galaxies too. If you have two galaxies that are gravitationally interacting with each other, oftentimes, given enough time, they are going to come together and they are going to merge. So the galaxies are going to merge. Their stars are going to become part of the same galaxy. Their gas clouds are going to collide with each other. And even their supermassive black holes at their center are going to eventually merge and become an even more supermassive black hole. Now, the fun thing is, of course, is that there's actually a lot of space between the stars. So when these huge galaxies smack into each other, you don't really have to worry about the individual stars running into each other. So it's not like solar systems are being wiped out by this process or anything like that. It's the gas clouds that are smacking into each other. And that's why these galactic collisions often look very, very bright like this. In this picture where you're seeing these big patches of pink, that is where gas clouds have collided. And that is a lot of new stars being formed. When gas clouds collide, it's good for making new stars. So what you'll often see in big galactic collisions like this is lots of new solar systems forming. And this is actually something that we see happening all over the place, but we can't watch one collision just play out because this process can take 1 billion years for two galaxies to finish colliding. And that means we can't watch a whole one. But because it's happening all the time, all over the place, we can actually look around and see galaxies in different stages of the collision everywhere we look. And by combining all those observations together, then we can get a full idea of how a collision looks. So here is, as we look out, here's a model of two galaxies getting ready to collide. And this is an actual photo of two galaxies in that stage of collision. And as the model continues, you'll see different parts of the collision represented by actual observations that we can make with our telescopes. And of course, we're seeing them at different angles because they're all over the place. So this is a process that, even though it happens over like 1 billion years, you can actually watch happen if you look all over the place. I'm going to pause here, Karen. Have any questions come in?
There's a bunch that have come in. So I'll start with sort of the more recent ones. And then if we have some time before you move on to the next section, I'll go back to some of the earlier questions. But somebody asked, can galaxies colliding create black holes?
So it's probably not going to create any black holes because black holes get created when large stars run out of fuel and blow themselves up as supernova. And nothing about the galaxy collision is going to make the star run out of fuel faster. But black holes that already exist can get bigger. So there's a supermassive black hole at the center of most galaxies. And when galaxies collide, those supermassive black holes will merge together eventually and become one giant black hole. So while it doesn't create new ones, it can make the supermassive black hole that's already there get more massive.
And this is a great one. A third grader asks, will our Milky Way galaxy ever collide with another galaxy?
I'm going to hold off on that one because I might be talking about that in a few minutes.
All right. So we'll go back just to one or two from earlier when you were talking about Hubble, and we had that sort of tie-dye looking image right at the beginning. Somebody asked, how deep can Hubble see? And how can scientists see the whole sky of the universe? Yeah, so it came in during this picture here.
So Hubble right now, that farthest galaxy it's ever seen was taken when that galaxy was about 13.4 billion light years away from us. So if you consider that the visible universe is about, light has had about 13.8 billion years since the beginning of the universe to travel, we can see about 13.4 billion years of that with Hubble. James Webb's going to be able to see even further. And what this was from a spacecraft called WMAP, or let's see how the auto caption does with this one, the Wilson Microwave Anisotropic Probe. I think that's what it is. And because it was in space, Earth wasn't really in the way. It could look in all directions. And the only thing it was looking for was this radiation. So it looked over the whole sky, not immediately. It took a lot of time for it to map the whole sky, but it did eventually get to see everything. And it found this radiation everywhere.
Cool. Maybe one more question before you move on?
Yeah, sure.
Ms. P's class wants to know, will the galaxies change if they don't collide with one another?
They will eventually change, just left on their own. And that has to do with the fact that galaxies go through star formation at different rates. So we know very early, for instance, very early in the universe, galaxies were forming stars a lot faster than they are now. As galaxies age, there's less free gas for them to form more stars. So although they're not going to grow necessarily without colliding with other galaxies, they will still change. They do age.
Cool. One more, or do you need to move on to the next section so you don't run out of time?
Let's do one more. That's fine.
Okay. What happens when things go into a black hole?
We don't know. We've never been inside a black hole. When things are falling into a black hole, what happens is the intense gravity of the black hole actually pulls the individual molecules in the object apart into a spaghetti stream of atoms, which we call spaghettification. As to what happens once it's in the black hole, we have no idea because we don't know what goes on inside a black hole because we can't see inside a black hole because not even light can escape it.
Cool. There are more questions, but I'll let you move on.
All right. So we were looking at this video, which is models of a collision, a model of a collision interspersed with images of actual collision between large galaxies. This is what we call a major merger. And here are some images of major mergers. When that happened, the resulting galaxy, the galaxy that formed from the two of them combining, does not look like the two galaxies that it started out as. The structure gets pulled apart. You saw the streams getting pulled out of those spirals. So when two huge galaxies collide, the thing that forms from them, the bigger galaxy that forms from them, looks nothing like the two galaxies that it started out with. So often when you get two big spirals colliding, you're going to wind up with an elliptical galaxy, which is a completely different shape. So you get something else. But there's also minor mergers. There's lots of really tiny galaxies out there, mostly tiny irregular ones. And if they combine with a really big one like the Milky Way, the big one doesn't change very much. It's more like the smaller one gets pulled apart and absorbed into the larger one. And this is something we can see, for instance, here. This is one of my favorite galaxies. This is the galaxy M51, or the Whirlpool. It's one of the most beautiful spirals in space. And you can see this sort of light blob next to it. That is another galaxy that is slowly being absorbed into M51, but it's not affecting M51. M51 still has this perfect spiral to it. So this is an example of a minor merger, where you have a very large galaxy and a very small galaxy. And this is something that happens quite frequently, is happening today to our Milky Way. So our Milky Way, we know, has absorbed many smaller galaxies into itself. And of course, our Milky Way still has its beautiful spiral structure. So it hasn't been very affected by it. It is, in fact, today, pulling a small galaxy apart. So here is an image. It's a galaxy. It's called the Canis Major Dwarf Galaxy. And, you know, it probably used to look like a cloud. Now it looks like a long stream. Anywhere where you're seeing this pink, that is the stream of what used to be this little dwarf galaxy that is now stretching all around the Milky Way, because the Milky Way has just pulled it apart and is pulling all of that gas and the stars and the dust into its spiral. So all of this is going to become a part of the spiral of the Milky Way, and the Milky Way itself isn't really going to be very affected by it. So, you know, this is happening all the time, and the Milky Way doesn't really notice, even though it does get a little bit bigger every time. And we do think, actually, a lot of these big spirals have clusters of stars that orbit them, which we call globular clusters. Some of those may actually be the leftovers of these little galaxies that the Milky Way just ate up. So for instance, here is one of the globular clusters that orbits the Milky Way. It's called the Omega Centauri cluster. And we think this is one of the bigger clusters that orbits the Milky Way. We think this used to be the core of a small galaxy. And the Milky Way pulled all the rest of it apart and absorbed it. And just the core is left, still orbiting the Milky Way. So the Milky Way is doing small, minor mergers all the time. What about a major merger? Somebody asked earlier, is the Milky Way ever going to collide with something else? So it's doing these little collisions with these small galaxies all the time, but there is a major merger in the Milky Way's future in a mere 4.5 billion years. So, you know, don't cancel your weekend plans. But we have a large galaxy near us called Andromeda. Andromeda is even bigger than the Milky Way, and they are on a collision course. So as you watch this video, which is going to be a model of that collision, you'll be able to see the time over here. 0 billion years means now. And we're going to project into the future to see what happens. So here is our Milky Way. And then over the next several billion years, nothing major happens to it, except that it gets closer and closer to Andromeda, which right now is a nice 2.5 million years. There's a third galaxy here, Triangulum. It's this little tiny thing. It's not really going to play a major role in this collision. So then starting about 4 billion years into the future, around this time, the sun is becoming a supergiant. So we've got other things to worry about here on the Earth. They're going to start dancing around each other. The spiral structures are going to get pulled apart, and the cores of the galaxies are going to start doing this dance until they eventually combine and merge. And those streams of stars and gas that made up the beautiful spiral arms of these galaxies don't have that spiral structure anymore. And what we're left with is this elliptical galaxy that doesn't have the beautiful structure of a spiral. It's something completely different from what it started in. So this is in our Milky Way's future. Again, you don't have to cancel your weekend plans. It's not happening anytime soon, but this is going to happen in the next several billion years. The Milky Way is going to undergo a major merger with Andromeda. And Karen, if any more questions have come in, I would love to answer them.
Yeah, I was just looking at the timestamp on that major merger, and realized the time it major merges, hard to say, the sun will be gone, likely.
Yeah,
so we really
Earth
don't have to worry about it. We had a question that came in just a few minutes ago, and I don't remember exactly which slide you were on, but Shane, who's in 5th grade, asked, what shape would it look like in 3D? Maybe you go back a slide or two, we'll know what we were referencing. Or maybe Shane can follow up with. Yeah, I'm not sure exactly.
Well, this shows, I'll play this video again. This sort of shows in 3D what the collisions look like. The spirals like M51, they look like dinner plates from the side.
It may have been when you were on the M51 picture.
So M51 right here, this is a spiral like the Milky Way. We're looking at it face on, sort of like this. If we were to look at it from the side like this, it would look very, very thin, like a dinner plate.
And someone had asked earlier when we were looking at one of the pretty galaxy pictures is, like, why is one galaxy kind of brownish and one is all purple, blue, and sparkly? Maybe just like note when we're looking at these images, are they real color, false color?
Yeah, so sometimes, so what we often do to get these gorgeous pictures is we combine pictures that were taken in several different wavelengths. So where you're seeing a lot of dark brown, that is usually meant to be the dust lanes, because galaxies are very dusty. That's good for us. Dust means planets can form. So, you know, we like that these galaxies are dusty, but like where you're seeing a lot of brown in some of these images, that is a lot of dust. Anywhere where you're seeing bright pink, like you're seeing here, those are very active areas of the galaxy. So that's a place where you're going to get a lot of star formation. You'll notice it in spirals, it tends to be along the arms. Anywhere where you're seeing a lot of blue, those are young hot stars. For instance, you can see this one has a lot of young hot stars in it. That means they can't be very old because those stars don't live very long. So there's a lot of star formation happening here as well. So that's sort of what some of the colors mean.
Cool. Well, I just looked at our time, and believe it or not, we are out of time. So I want to thank Talia for sharing all these cool things about galaxies. And I said, I think major merger is one of my new favorite space terms. Tongue twister, but fun nonetheless. So say farewell, Talia. Everybody's thanking you silently.
Thank you so much for your questions.
Yeah, questions and engagement is really what we all are looking for here at the museum. But I want to thank all of you for coming out today, tuning in for our virtual planetarium. These are happening every Tuesday at 2:30 for many months to come. So keeping an eye out on our social media channels. This is also some of the programs that we have used in our virtual planetarium shows. You can check those out as well. And I hope that you join us for a future one. So thanks, everybody. Have a great rest of your Tuesday.